Recording in progress.
Yeah, we'll see.
Yeah, buenos días. Good morning, everybody. We are going to proceed to the defense of the doctoral thesis from Maria Martinez Barbeito. The thesis is entitled, as you see in the screen, Power Grid Dynamics and Stability with the High Penetration of Renewable Energies, and has been supervised by Renewable and Camilla Gumila. In the examination panel, we are sitting here, the three of us, together with Dr. Mirnas and Barry, from the Department of Numerical Arithmetic and Prediction in the Fraunhofer Institute for Algorithms and Scientific Computing in Germany, and Maria Paz Tomec Moreno from the Department of Electrical Engineering, University of Zaragoza, and myself, Manuel Gómez from Electric Power Engineering in the Technical University of Catalonia, Barcelona. We are going to proceed to the defense. There will be a presentation of approximately 45-50 minutes, I suppose. Then we will do a very short break, 5 minutes break, and then we will continue with the discussion. Okay.
Yeah.
Okay. So yeah, you can start with it.
Okay. Well, hello everyone, and good morning. Thank you for being here. My PhD thesis is titled Power Grid Dynamics and Stability with a High Penetration of Renewable Energies, and I've done it under the supervision of Pere Collet and Damià Mila. So this is the outline for my talk, for my presentation today. First, I will give a brief introduction into the topic of power grids, as well as the motivation behind this thesis, and then I will move on to explain our work by focusing on different territories, as I did for the thesis document itself. So for Gran Canaria, we will see how we will analyze scenarios with increasing wind generation and secondary control. For the Balearic Islands, we will see how closing conventional power plants can affect the system, and also analyze scenarios with increasing photovoltaic generation. For Coxiara, we will see how we can use a small battery for frequency regulation, and for continental Europe, we've studied grid stability, in particular in scenarios with large power flows between different regions. And then I will just summarize the main concluding remarks of this thesis and discuss future perspectives of our work. So the aim of this thesis was to explore the path towards a fully renewable grid. And so since we need to decrease the CO2 emissions in upcoming years, we will see how the most contaminating power plants are progressively closed down and replaced by cleaner alternatives. And these alternatives, of course, include renewable energies, which will be deployed worldwide at very large scale. And also we will see how the degree of electrification across all sectors increases. And this transition towards renewable energies will change grid operation as we know it. So how does the grid work nowadays? Well, due to the lack of large-scale storage, nowadays the generation is adapted to the demand in real time so that they are balanced. And a good indicator of that balance is the frequency of the grid. So if there is excess of generation, the frequency goes above 50 hertz, which is the reference value. And if there is lack of generation, then the frequency falls below 50 hertz. And achieving this balance is possible because conventional energy sources are dispatchable, so they are controllable. However, variable renewable energy sources are highly uncontrollable and intermittent and unpredictable. And besides, conventional power plants have inertia and other control methods because they are basically large rotating masses, and because of that, they have mechanical inertia and they can store kinetic energy, and that helps to slow down frequency dynamics and dampen the fluctuations. However, variable renewable energy is integrated into the grid with power electronics, and they lack the physical inertia that conventional plants have. So these changes impose the need for new grid operation strategies, and so the changes that we have to make can be categorized into 3 main groups. So the most important is probably control. We will need to increase the amount of control in the system, both on the generation and on the demand side. And this can be achieved with storage by building overcapacity and curtailing the excess, with several demand management strategies and so on. And this is what we will see for the case of Gran Canaria and the Balearic Islands and Gobseada. And then also the transmission and distribution grids will need to become more flexible because traditionally generation is very centralized, but renewable energies are being integrated both at transmission and distribution level. So this means that in the future, the transmission grid will most likely need to accommodate very large power flows between distant areas. And this is what we will see for the case of continental Europe. And for that, high voltage DC technology emerges as a good choice. And also with the increase of distributed generation, we will see probably how at transmission level in some areas we have a near zero power flow, and also that the distribution network will need to support bidirectional power flows. And finally, forecasting of both demand and generation, of both demand and variable renewable energy sources. And this will allow for better planning, and better planning means better control. And this is something we have not analyzed and we have not looked into in the thesis, but it could be interesting as future work. So starting with Gran Canaria. Gran Canaria is an island in the Canary Islands, and its high voltage power grid can be mapped down to substation level as a network of interacting nodes and links, as you can see here, where the nodes are conventional power plants or substations, and the links are transmission lines. And Gran Canaria and the Canary Islands in general have trade winds all year round. So that makes wind the major natural resource there. And that is why we were interested in analyzing scenarios with increasing wind generation. So to do that, we developed a model. And yeah, we will model the grid as a network, as I said before, and each node in the network, the dynamics of each node in the network is described by these 2 equations here. So we have an equation for the voltage phase angle and an equation for the angular frequency. And in the frequency equation, you can see the balance that I was mentioning before between the generation and the demand. And we also have a term to account for the transmission from one node to all its neighbors. And additionally, for conventional power plants, we have 2 extra equations. So we have an equation for primary control and an equation for secondary control. So when there is a contingency, for instance here, if there is lack of generation, the frequency falls below the reference value. And that initial decline in the frequency is determined by the inertia of the system. And then primary control kicks in within seconds, so very fast, to stop the frequency from deviating more. And then secondary control is responsible to restore the frequency back to its nominal value. And additionally, we also have an extra term here in the secondary control equation. And this term allows us to mimic the dispatch, because it allows us to force the power output of a plant to a reference power. And this reference power will be the scheduled power for that plant. So this model takes some data as input, and this data is taken from the grid operator. This is demand and generation data, and it's publicly available. And so the demand is given at island level. So we distribute it proportionally to the population of each node. And then we add some correlated noise to model the faster stochastic changes of the demand. Then for conventional generation, we distribute it proportionally to the installed power at each plant. And for the renewable generation, we distribute it homogeneously among the renewable facilities. And so we use this data to feed the model. This is input for the model, and the model outputs the frequency of the grid. So we can compare that frequency from the model to actual frequency measurements, and these are taken from this database here, which is also public. So, yeah, the first thing that we have to do with the model is to validate it. And to do so, we take 2019 as reference. And as I said before, we take the power data as input, and the model outputs the frequency fluctuations, which are here shown in green. And we can compare those with actual frequency data, which is here shown in black. So we can see that the model is able to capture the frequency fluctuations that are associated to power changes here in the data, and especially we notice these large frequency peaks that are associated with the wind power ramps. And so, yeah, and that is for the time series. And we can also look at the statistics over a few days. In particular, we can look at the probability density function and the rank size distribution. And the rank size distribution tells us the probability of having a fluctuation larger than a particular size. So if we look at these both plots, we can see that the model works particularly well for the smaller deviations. And also here, we can notice that the frequency fluctuations are not Gaussian. They have higher probability of larger deviations. And looking at the power spectrum, we can see that the model works better for the slower timescales, and also this power spectrum supports our choice of correlated noise to model the faster demand changes. And because, yeah, it's flat here as white noise, and then it has a slope of -2, which is characteristic for a random walk. So with this, we can conclude that the model works well, and we can use it to analyze different scenarios. And as I said before, we focus on increasing wind generation. So this is for the reference case. This is the grid frequency fluctuations for the reference wind power that we have here. And we can see that in this reference case, the frequency fluctuations are small because, well, they stay within the 0.15 Hertz limit that we have here most of the time. So this is a safe operational regime for the system. However, as we increase wind generation in the system, we observe that the frequency fluctuations become much larger. And we can also, well, we see that in the time series, but also here in the rank size distribution. However, in some cases, the frequency fluctuations are actually smaller, as you can see here. And this is because of curtailment. So curtailment is basically discarding excess power. So when we have excess wind generation, we simply use the demanded amount and we discard the excess. And so this acts as another layer of control and reduces fluctuations. And this is also noticed in the rank size distribution here. And of course, this is beneficial, but only to some extent, because in the end, we are discarding power. So at some point, increasing more the installed wind power, the discarded power increases more than the used power does. So yeah, at some point it becomes, it's not really worth it. So as we saw before, these frequency fluctuations in these scenarios with larger wind generation are way too large. They exceed this 0.15 Hertz limit. And so we somehow need to increase the amount of control in the system. And we saw that by increasing secondary control, we are able to reduce the frequency fluctuations so that they are comparable to the reference case. As you can see here, by increasing secondary control, we change these frequency fluctuations from this to this, and this is comparable to this, which is the reference case. And we also see that in the rank size distribution, because the distribution for the case with more control is very similar to the reference case, which is shown here in the dashed black line. So we were interested in estimating these additional control needs, and we did that both numerically and analytically, but I will not go into the details of the analytical estimation here, both for winter and summer. And as you can see here, well, we did that, so numerically, we increased secondary control until the probability of frequency fluctuations larger than 0.2 is exactly the same as in the reference case. So basically, the probability of fluctuations larger than 0.2, well, this line, this vertical line marks that 0.2. And so we increase secondary control until the blue distribution, so until, well, the red one, which is the one with more control, crosses this vertical line as well as the reference distribution here. And so, yeah, we observed that by increasing we observed that the additional control needs increased linearly with the installed wind power up to a certain point. And at that point, we observe a plateau. And this plateau is due to the effect of curtailment. So curtailment, once again, reduces frequency fluctuations. So it reduces the need for additional secondary control. And that is why we see that here. We can also look at the stress of transmission lines, and the stress of a line basically tells us how close to its limits the line is. So it's the ratio between the power flowing through the line and its maximum capacity. And we can see here in the reference case that all lines are well below its limits, and the higher stress levels are observed here in the north, which is where the main consumption centers are located. In the case with more wind power, we observe that the stress now changes, especially in these lines, which are connected to the wind generation sites shown here with the square symbols and also with the arrows. And especially here, this short line in the south becomes overloaded. So this is something that we have to take into account and probably upgrade the grid in that area. So just to conclude with this part, we have seen that the model we've developed is able to reproduce the statistics of the frequency fluctuations to a good extent. And we have used that model to analyze scenarios with increasing wind generation. And when we do that, we observe larger frequency fluctuations. So we have to increase the control in the system. And we have seen that both curtailment and secondary control are effective at reducing the fluctuations. And we have also seen that the stress of the lines increases. So yeah, there is a higher transmission capacity needs. So moving on now to the Balearic Islands. The Balearic Islands are a set of Spanish islands in the Mediterranean, as you probably know. And and their high voltage power grid looks like this. So we have the 4 islands connected through AC cables. So this means that they are all synchronous. However, there is also a cable connecting Mallorca to the peninsula. And this is a high voltage DC cable. And this cable brings a large fraction of the power that is consumed in the islands. And since it is a DC link, this means that the Balearic system is asynchronous from the continental European system. And as many other territories in the world, the Balearic Islands have in their decarbonization agenda, they plan on closing conventional power plants. And this is precisely what they did in 2019 when they closed down a coal plant. So before the close down, we see here, we observed that coal was the main generation source, followed by the high voltage DC link, which brings around 30% of the demand, and then also combined cycle. However, after the close down, combined cycle basically replaced coal as the main generation source, except for short periods of the year where the coal plant, the remaining units of the coal plant are still used. And so basically natural gas replaced coal because it is less polluting. So we wanted to see how this affected the system. And so we looked at different days from the period before and after the close down. And as you can see here, from the period before the close down, when coal was the main generation source, this is the power mix then for a typical day. The frequency fluctuations are are quite large, and this also shows in the standard deviations and in the standard deviation, and compared especially to the case nowadays after the close down, we can see that we have much smaller fluctuations when combined cycle is the main generation source. So we concluded that this is because combined cycle has a larger control capability than coal, and that is why the fluctuations have been reduced. Moreover, we also noticed that in some cases, the frequency was staying fixed at the 0.15 Hz value for quite some time. And this was quite surprising to us because we did not expect this from the typical control mechanisms of power plants. And this was happening not only before the close down, but also after, as you can see here. And we noticed that when that is the case, the power of the link fluctuates a lot, as you can see here. The link has a rather constant profile. It has these very large step changes, but otherwise it's very constant. But during these moments, it fluctuates a lot. And so we concluded that the link is responsible for keeping the frequency there. So it has a kind of threshold control that is only activated when the frequency reaches plus or minus 0.15 Hertz. And there is a difference. There is a difference though between the case before the close down and after the close down, and that is that before the close down, the frequency fluctuations were much larger because coal was then the main generation source, and so the control from the link was activated quite often. However, nowadays this is happening less often, less frequently, and moreover, when we see that happening, the reason behind these frequency excursions in the first place is not recorded in the power data. So we cannot find any power change in the data that could lead to this frequency fluctuation. So we believe this is some kind of correction measure from the grid operator or something like that. So we can look at the statistics of before and after the close down also. And we can see here for these 3 days, just as an example, that before the close down, the probability of having large fluctuations was much higher than nowadays when we have this soft decay in the probability. And also we have this strong decay at 0.15 Hertz, which is due to the effect of the control from the link. And when we have days like January 30, we first have this initial soft decay, then we have a flat distribution here, and this is because the frequency is spending a very short time in for that frequency values, and then we also have once again the strong decay. And if we look at the distributions for the 3-month period, for the case before the close down, it's very similar to that of this day. So most days are exactly the same as this one. And for the period after the close down, we have a mix of days between like January 26 and January 30 here. So we have that initial softer decay, and then this shoulder-like shape caused by the activation of the link. And this strong decay in the probability of having larger fluctuations was also observed by other authors previously when they compared the probability density function of frequency fluctuations in different islands of the world. And while other islands of the world have these very heavy tails, the Balearic Islands have these strong cut. So and besides closing conventional power plants, the Balearic Islands, they plan on increasing photovoltaic generation. And so we wanted to analyze these scenarios as well. So we use the same model as before that we used for Gran Canaria. However, now we have an extra equation to model the link dynamics. And this And this equation basically, under normal operation, so when the frequency stays within the 0.15 Hz limit, this control term is 0. So we simply force the power from the link to a reference power, and this reference power is given also by the data from the grid operator. And then when the frequency goes above or below plus or minus 0.15 Hz, this control term is activated, and this C-link here is a large value, has a large value because the control acts very fast. So with this model, once again, the first thing that we have to do is to validate it. And to do so, we take the period after the close down. So here we compare the frequency fluctuations from the model to the frequency data from after the close down, and also both the time series and the statistics. And as you can see, once again, the model performs well also in this case. However, now we have to also validate the link equation, the equation that we use to model the link dynamics. And to do so, we actually have to look at the period before the close down, which was when the frequency was naturally larger. So that is when the control was activated more often. And yeah, we can see that by including the control, the term of the control, we are able to reproduce the behavior of the frequency. And especially we can reproduce this strong decay in the probability here. So yeah, once we have validated the model, we can use it to analyze different scenarios. And we focus on increasing photovoltaic generation, as I said. So we will be comparing 3 different cases depending on what we do with the conventional power plants once they are no longer needed. And we will be comparing those to this reference case where we have the power mix and the frequency, the simulated frequency. So in case A, we will always leave one power plant working at a minimum power so that it provides inertia and control. In case B, all power plants will stay connected even when they don't provide any power, but just to provide inertia. And in case C, we will disconnect completely all the power plants so that they don't provide inertia and control, and the only inertia and control left in the system is that from consumers and the high voltage DC link, the control from the high voltage DC link. So comparing those scenarios with increasing photovoltaic generation to the reference case, we can see that the fluctuations are much larger. However, the high voltage DC link, the control provided by the high voltage DC link, is enough to keep the fluctuations within the 0.15 Hz limit in all the cases. If we compare case A, B, and C among them, we can see that the larger inertia and control there is in the system, the less volatile the frequency fluctuations are. And we can actually see that better if we zoom in. You can see that here in this case, the frequency is varying very fast. And so although we are able to keep the frequency within the 0.15 Hz limit, it would be advisable to keep some inertia and control in the system just to avoid this such high volatility. In this case, we can also look at the stress of transmission lines. And we can see here, this is for the reference case, and we can see that all the lines are well below its limits, and the highest, the one with the highest stress is the high voltage DC link, but anyway, it's below its maximum. However, once we increase photovoltaic generation, we see that the stress levels change, and in fact, they go over over one here in some lines, indicating that they are overloaded. So this is once again something that we would have to avoid, and we could either upgrade the grid and or distribute more the photovoltaic generation. As you can see here, this also works effectively at reducing the stress of transmission lines. So that's something we could do. So just to conclude with this part, we have seen that closing conventional power plants can significantly change the behavior of the frequency. And once again, we have used the model to, we have seen that the model reproduces the frequency statistics, and especially the equation that we use to model the link dynamics works well. And we have seen that, we have analyzed scenarios with increasing photovoltaic generation, and we have seen that in those cases, the frequency fluctuations become large. And we have also analyzed scenarios with reduced inertia and control. But even though we reduce inertia and control, the high voltage DC link control seems to be enough to keep the deviations within the limits. And finally, we have also seen that the stress of the lines increases, but distributing more photovoltaic generation could help to reduce that stress, such high stress. So moving on now to Gökçeada. Gökçeada is the largest Turkish island, and it is part of this European project called BPP for Islands, which aims to analyze the specific challenges that islands face with regard to the energy transition. And this is the power grid of Gökçeada. You can see there is a conventional power plant in the island, but it is also connected to mainland through an AC link. And actually, this AC link, together with the 2 wind turbines in the island, are responsible for covering almost the totality of the demand. So our work with Gökçeada began as part of this project. And so we used the same model that we presented before to analyze 2 different modes of operation. So we analyzed a case where the island is connected to mainland, so the AC link is active. And we analyzed another case where this AC link is not operating, so the power plants in the island have to provide the demanded power. So starting with the grid-connected case here, we can see that the model gives very small frequency fluctuations, and this is because we are modeling the continent as a node that runs constantly at 50 Hertz, so it has no fluctuations. So the model is basically telling us that the frequency in the island is deviating, is not really deviating from the frequency of the continent, and this is because the island is connected through a AC link. And in this case, in the island case, where the conventional power plants have to provide the power, we can see that the frequency is now larger, and this is the result of that conventional power plant adapting to the changes in the demand and in the wind power ramps. We can also look at compare the stress of lines, and the most noticeable change, besides having this AC link connected or not, is in these lines here, connecting this node that is connected to mainland and to the wind turbines, to this area here, which is where the main consumption centers are located. So in this case, where the island is connected, these lines have to carry all the power from the AC link as well as the wind turbines. However, in this case, they simply have to carry the power from the turbines, because the power plant is already located quite close to that area. For Gökçeada, we have also analyzed how we could use a battery, a small battery, to provide frequency regulation. And we did this motivated by the fact that sometimes in Gökçeada they have synchronization problems, especially when they have the 2 wind turbines connected. So to do that, to analyze this, we used a simpler model where we don't have the grid, and we simply model the grid as a large generator. So we have an equation for the frequency, primary control, and secondary control. And now we also need a model for the battery. So we model the battery with these 2 equations. We have one for the power and one for the charge. And this power equation is basically like a primary control, but we have this term here, which allows us to keep the deviations of the charge close to the set point value. And one important thing here is that the battery, of course, the power and the charge have to stay within the limits of the battery that we are considering. So we ran some simulations for different values of the gamma parameter here in these equations. And this gamma parameter controls how much the charge deviates from the reference from the set point charge value. So the larger the gamma, the less the battery the charge deviates. And so we start here with a gamma equal to 1. And yeah, we did this for a small battery of 50 kilowatt hour. And so starting with this case, for gamma equal to 1, we have here the power mix. And this is the input data for the model, the grid frequency given by the model, the rock-off, which is calculated from the frequency, and also the battery power and the battery charge. So we can see that by including this small battery with a gamma equal to 1, we are able to reduce the frequency fluctuations but not very much. And however, the rock-off is quite reduced, and this comes at the cost of having very small deviations of the power as well as the charge. However, when we decrease the gamma, we can see that now we are able to reduce the frequency fluctuations more, and also the rock-off is more reduced. But once again, the cost is now having larger deviations both of the power and the charge. And if we reduce gamma even more, we can see that the fluctuations are now much more reduced. And however, now the battery is even reaching its limits in some cases. And that is why we observe these peaks in the rock-off. So if we zoom in one of those peaks, we can see that what is happening is that the battery is now at its limit, so it cannot absorb any more power. And because of that, the frequency fluctuations are exactly the same as in the case without the battery, but they are just simply shifted. And because of that, the rock-off is exactly the same. Yeah, so yeah. We can also look at this from a statistical point of view. We have the rank size distribution of frequency fluctuations here and of rock-off fluctuations here. And we can see that as we decrease the gamma, we are able to reduce the frequency fluctuations. However, for the rock-off, at some point, decreasing gamma almost has a negative effect because we see this larger probability here, and this is due to the peaks that we were discussing before. So we performed a more systematic analysis for more gamma parameter values, and this is what we saw. So we have here the standard deviation of the rock-off and the standard deviation of the frequency, as well as the energy accumulated by the battery in one day and the depth of discharge for different gamma parameters. So we see that as we decrease gamma, we are able to reduce both the frequency and the rock-off, but this comes at the cost of having the battery accumulating more energy and also having a larger depth of discharge. So what is the optimal value for gamma? Well, it depends. It depends on how much we want to decrease the frequency and rock-off fluctuations, and also it depends on the price we are willing to pay, because using a battery in the end reduces the lifetime of the battery. And so we actually estimated battery wear from the depth of discharge and the number of cycles per day. And we saw that for a gamma of 0.01, the battery could last for 19 years until its capacity is reduced to 70%. And so 19 years is a long time, and this is actually more than the lifetime of a typical battery. So using the battery for frequency regulation does not reduce much the battery lifetime. So just to conclude with this part, we have analyzed two different grid operation modes, and we have seen that they have large differences, especially on the size of frequency fluctuations. And we have seen that using a small battery can be helpful for frequency regulation, because it reduces very effectively the fluctuations of both the frequency and the rock-off. So, and yeah, we have seen that using the battery for frequency regulation does not reduce much the battery life. So moving on to continental Europe. For the case of continental Europe, of course, this is a much larger system than the islands that we have analyzed before. As you can see here, the grid in continental Europe has almost 4,000 buses, and there are several generators of many different technology types. And so for this case, we were interested in analyzing grid stability, and especially in scenarios with large interregional power imbalances. And we did this motivated by the fact that as renewable energies are being deployed, and there are some geographical areas that have more renewable potential than others. So the grid in the future, the transmission grid, will need to accommodate very large power flows between these distant areas. And this has shown to be a problem in the past. As you can see here, in 2019, we had a grid split here in the Balkan area. And this grid split was caused by a situation of large power flows between this area here and Central Europe. So we were interested in analyzing grid stability, and to do that, we used a simpler model than before. So in this case, we don't have secondary control because the demand is kept constant, and primary control is instantaneous. So in the end, it's modeled by this damping term here. And the fixed points for this system are given by these two equations. And as you can see, the fixed points depend on the phase difference. So this means that if we add the same value to all phases, we just will obtain another non-isolated fixed point. And this means that the Jacobian matrix will have a zero eigenvalue. So we performed a linear stability analysis for this, and it can be shown that the fixed points can only be lost through a saddle node bifurcation when a second eigenvalue of the Jacobian vanishes, and this happens also when a second eigenvalue of the Laplacian vanishes. And the second eigenvalue of the Laplacian vanishes when this condition is fulfilled, so when this sum is zero. This sum runs over all spanning trees of the graph. And here we can distinguish two scenarios, two cases. So if the phase differences in all the lines are below pi/2, then this sum here cannot vanish because all these terms will have the same sign, either positive or negative. So the system is stable. However, if a line goes above pi/2, then we have two scenarios. If that line is the single line connecting two areas of the network, then that line is part of the spanning trees of all the spanning trees, and so all terms in the sum are zero, and that is how instability emerges. However, in scenario B, since when we have this line, which is not the single line connecting these two areas, in that case we can observe phase differences above pi/2. And what happens is that when the line reaches pi/2 and goes past pi/2, its power flow starts to decrease. So the phase differences in the other lines starts to increase to compensate and to transmit more power from one area to the other. But at some point, increasing the phase difference does not increase the power from one area to the other. And that is how the instability emerges in that case. So we analyze scenarios with increasing power imbalances, and we did that by, starting with the reference dispatch, we simply increase progressively the generation in some area, in this case here, just as an example, and decrease it in another area here progressively. And we do that, and we continue the fixed point while we do that. And so we see that initially, these are the least damped eigenvalues of the Jacobian, and we point out especially these pair of complex conjugate eigenvalues, which have this eigenvector, and this eigenvector here has large. This is just the phase components of the eigenvector, and they have large components here in the Iberian Peninsula and in the Balkans, and small components in Central Europe. So we see that this mode is responsible for large antiphase oscillations between the Iberian Peninsula and the Balkans. So these are the inter-area oscillations. And as we increase the imbalance in the system, we can see how the eigenvalues and the eigenvectors evolve. And so we do that and we see how this pair of complex conjugate eigenvalues at some point becomes real. So their imaginary part becomes 0. And so they suffer a Velyakov-Devaney transition. And then after that, they separate very fast. So one moves toward negative values and the other one goes towards positive values. And when that one reaches 0, that is when we have the silent node bifurcation. And at that point, the mode, the eigenvector is now real, and it shows that there is a splitting here in the Pyrenees. And we can also do some simulations, some short simulations to understand better what is happening. So we have here 2 cases. In one case, we increase the imbalance in the system to another value that is below the critical imbalance. And so the system initially, we observe fluctuations, but in the end, we reach another fixed point. However, if we increase the imbalance past the critical imbalance, then we observe that the frequency separates, and then we observe large incoherent oscillations. So, yeah. We can also look at the fixed point, comparing the reference case and the case just before the instability here. And we observe that initially all phase differences are small, and in fact they are below pi/6 here. However, before the imbalance, we observe that there is a line here in the Pyrenees that is above pi/2. So this is a scenario B that I was explaining before. So what happens is, after this line goes above pi/2, its power flow starts to decrease. So the other lines start to increase their phase difference to compensate and transmit more power between these 2 areas. However, at some point, increasing the phase difference does not lead to more power flowing through these lines. And so that is when the instability emerges. And because of that, we can say that the instability is not really due to a lack of transmission capacity, because the lines are not really fully loaded, but due to topological constraints. And so to avoid this, to move past this initial instability, we came up with this mathematical trick where we will fix the power flow of one line to its maximum power flow once it reaches pi/2. So by doing that, we are able to continue the fixed point for larger generation imbalances. And as you can see here, then the final instability, so we will reach at some point an instability, and that is when all the lines connecting these 2 areas are fully loaded. So and so this trick, this mathematical trick, allows us to find a cut set. It allows us to find the set of lines that cuts the network into 2 areas, and in this case, it is these 4 lines here. So we also did that for another case, and in particular, it is this case here where we increase the generation in the Balkan area and decrease it in Central Europe. And this case, this situation resembles the situation that led to the splitting of 2021. So we do that exactly in the same way as we did before for the imbalance between the North and the South. And we see that, once again, this mode is the one that becomes unstable, but now it shows a splitting here in the Balkans. And we observe an initial instability where one line is above pi/2, while the other ones are not fully loaded. And then by applying this mathematical trick, we are able to identify this set of lines that cuts the network into 2. And these are the most critical lines in the transmission between these 2 areas. And the important thing here, the interesting thing here, is that this is not the minimal cut set. So we could cut the network just by removing 7 lines, but instead we are able to identify 8 lines. And we also did a more systematic analysis of different scenarios and using different initial conditions, different imbalance regions selected at random, and so on. And we summarize the results here in these two plots. So we have the average stress of all the lines and the ratio, the fraction of times each line is converted to DC. So it is, we apply this mathematical trick in those lines. And we see that the most vulnerable areas in the network are the Pyrenees and the Balkans. And actually, when we perform this systematic analysis of many, many scenarios, most of the times the grid either splits in the Pyrenees or in the Balkans, and in exactly the same way. So the same unstable eigenvector and everything is exactly the same. And these are actually areas that are known to be vulnerable places of the network. The Pyrenees, the Iberian Peninsula for geographical reasons, and the Balkans for historical reasons. However, we are also able to identify other lines that are important in the transmission between distant areas. And finally, I wanted to just quickly mention the work that I did during my research stay in Switzerland in the group of Philippe Jacquot. And we analyzed fault propagation and how inertia and damping affect a fault propagation. So we have here, just as an example, we analyzed a case where there is a fault here in Spain, and then we monitor the frequency in Portugal, in Central Europe, and here in the Balkans. And so we analyzed two different cases. The darker color here represents larger inertia near the fault, and the darker color here represents larger damping near the fault. So we can see that by including inertia, by having more inertia near the fault, we are able to reduce the frequency nadir and also the rock-off, but inertia favors the propagation of fluctuations, as you can see here. And for damping, damping reduces the amplitude of oscillations in general. So this could be interesting, especially to reduce inter-area oscillations, which can be tricky sometimes in grid operation. And we have shown that by increasing damping in strategic regions, we can effectively reduce inter-area oscillations. So to conclude with this part, we've explained how stability is lost when a second eigenvalue becomes zero. And we have seen two scenarios depending if there is a line that connects two parts of the network. So when its phase difference reaches pi/2, that is when we have the instability, or if there are more lines connecting the network, those two parts, and so we can observe phase differences larger than pi/2. And we have analyzed different scenarios characterized by large power flows between different regions, and we have seen that instabilities emerge not really due to a lack of transmission capacity, but due to topological constraints. We have seen also how the modes of this system provide information on which are the most vulnerable areas, and we have developed this mathematical trick to identify the most important lines in the transmission and the lines that split the network into two. And we have also analyzed the role of inertia and damping in fault propagation. So just to summarize the main the most important points of the thesis, we've developed a versatile model that reproduces the frequency statistics to a good extent, and this model allows to assimilate that data over very long periods in short time, because it runs quite fast, and it reproduces the dynamics of the frequency from timescales of seconds up to even months. So it can be used as a test bench to study the grid under different scenarios. And so for the case of Gran Canaria, we saw how we can increase wind generation and control. For the Balearic Islands, we saw how conventional power plants can really affect the system. And for also we analyzed cases with increasing photovoltaic generation, cases with lower inertia, but how the high voltage DC link would keep the fluctuations within range anyway. For the case of Goxeada, we have analyzed how a battery can be used for frequency regulation. And for the case of continental Europe, we have analyzed the stability of the grid in scenarios with power flows between distant regions and also fault propagation. So just as, just to conclude, we could, as future work, focus on, well, many different things, but we could start by extending the model to represent the grid in a more accurate way. So we could include things such as lines with losses. We could also model voltage dynamics, especially for the faster timescales. We could include lower grid levels, especially since distributed generation is increasing, and also model the dynamics of power electronics since conventional power plants will progressively be closed down. We could also implement other control methods such as large-scale storage, different methods of distributed control, different demand-side management and demand response strategies. Also, we could focus on forecasting of both demand and variable renewable energy sources. We could also focus on the use of electric vehicles, especially since they can also provide grid services. And well, we could also analyze other scenarios such as cascading failures and blackouts and so on. So yeah, that is all that I wanted to say. Thank you.
Thank you very much for the presentation. Well, now we will do a short break, 5 minutes, and then we will continue with the discussion.
Okay.
So we will be back.